Our main goal here is to understand the behavior of a system qualitatively, as in how do the solutions change when we change a parameter? And so what kind of bifurcations can the system undergo? And so we're really interested in these different, qualitatively different bifurcations, saddle node, transcritical, and pitchfork in our case. And that raises the question now, so we've done that for one system, but what happens if the system is slightly modified? If you slightly change the parameters in the system, there could be other parameters, not just this control parameter that we're moving. And moreover, you could also imagine, well, the system is actually slightly different than what we wrote down. There could be additional terms in the equation. And the question is, do these bifurcations persist in terms of their overall structure? Or does the nature of these bifurcations change? Can they change when you add additional terms? And so we're looking at the structural stability of the bifurcations. Now, of course, I should emphasize, we're thinking of small changes in the equations. So we only slightly change the system. If we make large changes, then anything goes. So that's not very interesting. Okay, so let's do that with two examples. And one can do other examples further, but we just start with our saddle node bifurcation. And we want to see whether, when we change the equation, does this bifurcation disappear? Does it change its character? What happens? Okay, so we assume we have our equation again as before, x dot equals f of x and mu. But let's assume we have actually an additional parameter delta. And for delta equals 0, we get the original saddle node bifurcation. Whereas if delta is not 0, then something else could happen. And so we assume delta is small, and so we can do our expansion in delta in addition to the expansion in terms of x and mu. Okay, so we get for the saddle node bifurcation, we get then therefore mu plus x squared, where I suppress the coefficients that could be there in front, that they don't make any difference. Plus, and now the changes that in f due to a change in delta, and we only keep the linear term in delta. And so now, of course, f depends on delta explicitly, so that there's a term like df by d delta. But we also want to know what happens to the derivatives with respect to x and mu when you change delta. And so we get mixed derivatives like df by d delta of d mu times mu. Right? So this is times mu times delta. So that's the mixed derivative. Then similarly for x. And since we actually keep here all the way to x squared in our saddle node bifurcation, we should keep the corresponding term here, which would be d3 f d delta dx squared times x squared. And then there would be other terms which would be of higher order terms. Okay, so this is some kind of a mess. And so what do we want to ask? Well, we'd like to know whether this equation is equivalent to a saddle node bifurcation equation with maybe slightly shifted parameters, meaning slightly shifted mu, and maybe slightly shifted x. Or is that equation actually not, can we not cast it as a saddle node bifurcation equation? Okay, so let's look at what we have. A saddle node bifurcation would consist of, the equation consists of a constant term and term quadratic in x. So let's see, what do we have now? We have a constant term in mu. Then we have actually a term that's independent of mu. That's a new term. Then we have a linear term in x and a quadratic term in x. Okay, so what we'd like to have, we need to get rid of this term by introducing different coordinates, shifting x, for instance. And we'd like to get rid of this term by shifting coordinates, maybe mu. Okay, and so let's maybe sort things first so we see what we actually have. And so we get here x squared times 1 plus, where's the x squared? 1/2, the third derivative term, plus, and then we have a term with x, which is new, which we don't like, so to speak. That would not be matching our normal form for the saddle node bifurcation. So where's the x? So that's a d2f by d delta dx. And then we have a term with mu, which is 1 plus d2f by d delta d mu. And we have still the constant term delta df by d delta. So here's a delta missing. So we'd like to have this again in the form like the Sandler bifurcation. So we want to have a quadratic term in the dependent variable and a linear term in some other control, possibly other control parameter. So let's see. So we'd like to write it in this form that we have x minus a delta x naught squared. So that would shift the coordinate in x and would generate a quadratic term. And since we have already an x squared term, the term in front must be this cubic derivative. Okay. This, of course, generates not only what we want. So let's see, what do we want? The x squared is this term. Then we have a mixed product, x times delta x. That will generate a linear term in x. Very good. So we can now determine delta x so that 1 times delta x is this. That will compensate for that. Good. And then we have to square it out. So we get a delta x squared. But the delta x will be of order delta. And so therefore the delta x squared will be order delta squared, and we'll throw it away. Similarly, I think I forgot something here. There's a delta here because this term comes from over there, and we had an overall delta term here. Here, I did not forget that, so it's okay. How about here? Here, I forgot it also. Okay, so therefore now we see that when we square this out, here's this delta term. When we square this guy out, we also get a delta squared. So this times the delta x will also be higher order. So we really have just doing this, the delta x simply generates this. And we can write down what delta x has to be. Delta x naught has to be equal to minus 1/2 delta d by delta by xf plus higher order terms. That's essentially just this term, right? Okay, and similarly, we then want to absorb this constant term here in a shifted mu. And so we want to have something like 1 plus delta d2f d delta d mu times mu minus mu naught. And this mu naught now absorbs this. And so if you look at it, the mu naught, actually not mu naught, delta mu naught is minus delta d delta f plus higher order terms. Okay, the algebra here is not very important, so you can check that. Maybe there's a factor of 2 wrong, I'm not quite sure. But that doesn't, the point is that we actually managed to introduce a shift in x and the shift in mu. And then we have the same form of the equation again. We have a control parameter. We could call this, to make it more explicit, we could call this here a mu tilde. We could call this an x tilde squared. And we would have, again, a Sandler bifurcation equation. So in other words, even if we change the function f slightly, the Sandler bifurcation does not go away. It doesn't change its character. At most, it gets shifted. So to speak, you could make a little sketch. So right now we had, if this was our mu x coordinates, maybe we had a Sandler bifurcation like that. And so once we turn on delta, maybe what happened is that the bifurcation shifted over there. And so the bifurcation itself is at a slightly different value and the x values are different, but the overall structure is the same. So the conclusion is that the Sandler bifurcation is structurally stable. Is structurally stable. So that's a very robust object. Okay, good. Well, let's move on. We also had the transcritical bifurcation. So let's do the same thing with the transcritical bifurcation. So let's see how that works. Well, let's just start a new page. So there we have the original equation is x times mu plus x. And again, let me see, let me actually keep the coefficients so we know where which terms come from. So that's our transcritical bifurcation. And we now add again perturbations in F. And so there's, of course, dF by d delta. Then there is dF by d delta and dx times x. And there are additional terms. I'm not going to write them down because what I'm really focusing on is the following. A key feature of the transcritical bifurcation is that everything is proportional to x. Right? That reflects the fact that a transcritical bifurcation arises if we have a fixed point that persists for all value of mu. Now, if we change f in an arbitrary fashion, then we get also this term, which is not proportional to x. And therefore, it actually breaks that special feature of the transcritical bifurcation. And so I want to see whether this really makes a change in the transcritical bifurcation, or can I absorb that again as before? Okay, so let's continue as before. So we look at this equation and we essentially solve for x. And so if I combine this in a nicer form, so I have bx squared plus a mu plus delta d2f by d delta dx times x plus delta df by d delta. And I'm looking for fixed points, so I'm looking for zeros of this. And if I do my standard quadratic formula, I get the expression 1 over 2b times minus a mu minus delta dx delta. I mean, let me not use that short note. Minus delta times df by d delta dx plus minus the square root of a big thing, which is a mu plus delta d by d delta dx f squared minus 4b delta d delta by d delta f. Let me see, this is not very clear here. This is an important term, so let me make sure I've written that correctly. This is df by d delta. Okay, so what can we see? Well, the key feature of a transcritical bifurcation is that we have one solution which exists for all values of mu. If you again use our standard coordinates, mu and x. And there's another solution which sort of intersects this, so to speak, and there's a point where they merge. So the transcritical bifurcation is really this object here, right? The intersection point. And so the question is that preserved even when delta is not 0? And so that requires that both solutions are equal for some value of mu. So that means the square root has to vanish for some value of mu. So let's see, there are two cases. Let me shift it up. If, let's say, 4b delta df by d delta, if that is positive, what do we have? In that case, when this is positive, this actually, the term here is actually negative. And then there exists a value for mu where this square is 0. and that means the square root becomes imaginary. So in other words, in this case here, there is a value of mu where the solutions don't exist. And so that means there's a range in mu here. When the range comes about because whenever this is larger, I mean, as long as this thing here is smaller than that. So there's a range in mu where there's no solution. When you look at that more carefully, it's not hard, but I won't do it here explicitly. What it means is that instead of, now let me just sketch it. You get branches that look like that. So now you have a range of mu values where there's no solution at all. Let me maybe make a general comment here first. Delta is small, right? We assume delta is small. So in the limit delta going to 0, we need to get back to the original bifurcation diagram. So that means the changes will all be small when delta is very small. And so that means far away from where x is not small, the changes will be imperceptible, will be very small. So far away from the bifurcation point, whatever changes there are, the blue and the black curves should be the same. It's only in the vicinity of the bifurcation point where something will happen. And that's where, in this case, for this sign of the coefficient df by d delta, there's no bifurcation at all. There's no solution at all. So let's maybe write that down. So here, the transcritical bifurcation transcritical bifurcation has been replaced by 2 saddle node bifurcations. Okay, so that's interesting. What happens for the other sign? Well, let me make that sketch here. So again, this would be the unperturbed situation. And now let's say we have 4b delta times df by d delta is negative. Well, if that's negative, what happens? This is negative, then this whole thing is positive. That means the square root can never be 0. So that means there's no value for mu where both solutions are equal. Well, again, if you do a more careful analysis, you see the following, that instead of having a transcritical bifurcation, you simply have that this branch connects smoothly with that, this branch connects smoothly with that, and there's no bifurcation left. No bifurcation left. And so the upshot is the transcritical bifurcation is not structurally stable. No, sorry. So what does it mean in terms of practical implications? Should that mean that we should just say, well, transcritical bifurcations are, nice mathematical, games, but they're not really relevant because as soon as you change a parameter just a little bit, this bifurcation is actually not exactly that way. Well, of course, one thing could be, of course, if df by d delta, if that was 0, then nothing would happen. So that may be a construed argument. It's more important to say the following. Away from the original bifurcation point, right? There's a bifurcation point. Away from that, there's really very little change. And similar here, I didn't draw that very nicely in that way, but if you go far away, the blue and the black curves become the same. And so that means if you, let me just draw new bifurcation, so to speak. So imagine you actually measure now bifurcation in numerical simulations or in experiments. Well, you maybe would see something like that and something like that And well, maybe if it's numeric simulation, maybe you can also calculate that there's actually an unstable solution here. And it would look like this. And only when you go in, okay, here you would also find an unstable solution. And so that's pretty much a transcritical bifurcation. Only if you zoom in very close to this region here, you would see that maybe in this case, actually what happens is goes like that, goes like that. There's not truly a bifurcation. But if you don't zoom in, it's just as good as a transcritical bifurcation. So you still see, the bifurcation analysis that we did will still give you an important insight into what's going on. Okay, you can do the same thing with the pitchfork bifurcation, and you'll see that the pitchfork bifurcation is also not structurally stable in that sense. And that analysis is a little bit more involved, and we won't do that right here. Let me close by mentioning a word. As more often, it's good to know what the words are. So the transcritical bifurcation, we know it's robust if we only consider perturbations that respect that special feature that x equals 0 is a solution for all parameters, right? So in that class of functions, it's robust. It's only if we go to a more general class of systems, then this will not be robust anymore. In that more general class of systems, the transcritical bifurcation would be called degenerate because you have to tune a parameter somehow special to have this bifurcation occur in that form. And the special tuning is, of course, exactly that. You have to ensure that x equals 0 is a solution for this whole range of mu. And similarly, the pitchfork bifurcation in a general system would be degenerate, but in a system that has reflection symmetry, it would be robust. And if that reflection symmetry is broken only a little bit, then, well, it's not really a pitchfork bifurcation anymore, but it looks very much like one. And I think we can get back to that or look at an example at some later time. Okay, so that's all for checking the stability, structural stability and robustness of bifurcations.